All right, so welcome back. All right, this lesson, let's take a look at Boyle's law, which is essentially it's sort of a focused idea. We're looking at the certain conditions of gases. So gases exist under constant changing dynamics. Here, what we're doing is we're assuming that there are some dynamics that are changing, but we also have to assume certain constants, certain things that are not changing. We'll take a look at all the dynamics together in one in a later lesson, and I'll have that linked for you. So what we have to do, though, is for Boyle's law, we have to assume some constant conditions. I forgot how to spell the word condition. Constant conditions. All right, so some constant conditions. So one, if we're looking at relationship between pressure and volume, then one of our constants is probably going to be the temp, right? And remember, temperature is always a capital T, and well, I'll do this. So we're assuming a constant temperature, so there is no change in temperature. And of course, we measure that in degrees Celsius. Okay, we're going to assume degrees Celsius. So we'll find later that we will not use that in certain calculations, but for the purposes of this video, it works just fine. So, and we'll look at what the other condition is here in just a moment after we look at this concept. So let's think about this for a second. Let's take something, a container, and I'm making this up. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've just put 10 particles in there. Well, you wouldn't have just 10 particles, but was just 10, easy number to work with. I could, instead of writing 100 or 1, right? 10's an easy number to work with. So we put this into a container, and we have some way of pushing down on that. Let's just say that this is a plunger. Okay, let's just say this right here is a plunger. So right here, this represents a certain volume of space. And right here, from here to here, represents X amount of pressure, right? So now let's think about it this way. Let's change the condition. Same container. No, it doesn't quite look the same, but just assume it's the same container. All right, and we all of a sudden push the plunger down to here. We essentially compress those gases in that space, right? So there's still those 10 particles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So there's still those 10 particles that are there. And remember, here's a certain amount of volume, correct? So let's think about this. We had what we call an initial state. And then we have our changed state. State being the condition in which the gases are subjected, right? So if we look right here, this compared to this, there's a greater volume here, and there's less volume here. We can visually see that, and you've done this all your life. You realize, if you push on something and push it closer together, you may not be able to see those particles, but you realize that, hey, I've pushed all those particles closer together, and to do that required you to press. That's a force, right? So let's think about this. As we decrease the pressure, the volume, we had to increase the pressure. So conversely, here, when there was an increase in pressure, increase in volume, there must have been a decrease in pressure. Okay? We can visually see that. And if you keep that in mind here, this basically is the concept of Boyle's law. So we have two states. We have the initial state, state 1, and then we have the change state, state 2. It doesn't matter what you call it, initial, change, initial, final, 1, 2, it's all basically the same thing, right? So let's think about this. Let's think about this for a second. Let's mathematically relate these images in what we know to be true, because we've done this all of our lives, right? So that means we had pressure that was proportional to, let's think about this. If pressure is decreased, volume is increased. That is not a direct relationship. That is what we call an inverse relationship, right? It's an inverse relationship. So if, knowing that that is true, if we take the inverse of the volume, it should relate to the amount of pressure that's being applied. So now if we think about this graphically, right? If we think about this graphically, so you've got your volume, and typically we measure in liters, and you've got your pressure, and when we're talking about gases, if you think about it, we're in an atmosphere. So atmospheres is a unit for pressure. Now there's many units for pressure, and we will work back and forth between those units. But essentially those units, just like you're measuring in inches or feet or centimeters or meters, the same distance, this amount of distance is X distance, but the numbers change if I use a different unit. So the same is going to be true when we talk about pressure. The number will change when we talk about a different unit in pressure, but essentially the magnitude of it, the value of it, what it represents, it has to be the same, right? And so a simple way of looking at of pressure is to say atmospheres. Okay, so we're just assuming like 1 atmosphere pressure, right? The atmosphere that's like pressing it down on us, right? If pressure is inversely proportional to volume, then that means that we've basically got something that looks like that. Now we don't have to have numbers here, but we know that this relationship has to be true. Go back to your basic math, we know that this right here has to be true, right? Now, let's think about our conditions here. What else was constant besides temperature? And it had to be the amount of particles. Okay? It had to be the amount of particles. And in chemistry and physics, when we talk about the amount of particles, you guessed it, you're always talking about moles. So even though in this example here I only drew 10 dots to represent 10, say, molecules, we're really talking about moles. You need to always be thinking of moles of substance, because these things are a bunch of atoms that are sort of chemically bonded together, right? And so when we're talking about these different gases, so if we're not just talking about the effects on 1 or 2 molecules of that, we're talking about the effects on moles of that substance, right? So you need to keep that in mind, that when we're talking about amount of particles, we are talking about moles. Okay, we are talking about moles. Now, this whole idea of a constant, temperature is involved with all this, but we assume some sort of constant variable. Now, the idea of a constant, mathematically, we assign it a variable k. That's a lowercase k. Okay, it's a cursive lowercase k. You can write just plain old, like a k if you want, but that can look like a capital K. This is lowercase k. Oftentimes you'll see it that way, unless it's typed. So if we think about this, we've got all of this times whatever the constant is. We don't know what it is. We don't know what its value is. It doesn't matter because it's constant. So whatever that multiplier is, it would always stay that value. Okay, that we know is true. All right? If you go back to your basic math, you realize that this makes sense. So that means we've got pressure equals the inverse of volume times our constant. Okay, times our constant. All right, let me remake that for you, just so that looks, there we go, looks a little neater. Okay. So now if we think about this, that means that the constant would have to be equal to pressure times volume, right? If you just do your basic math, times volume on this side, so times volume on this side, we would get K times 1, which is K, equals pressure times volume. So we get this iteration, this form of this equation right here, all right? So what that means is, so we've got an initial state, right? So if you think about it, we've got the pressure times volume equals the constant. Here we've got pressure times volume equals a constant. But let's think about this. This was our initial state, and this is our secondary state, the new system, the change in the original condition, right? So now we can go back to what we've learned about in our math, and we realize that pressure times volume equals K. All I'm doing is bringing that down. Well, we also have over here K equals pressure times volume, but it's the new system. These two things are the exact same variable. So if you think about taking those two equations, we bring them together, we basically have the initial equals the final. And this right here is how we tend to view Boyle's law. Okay, this is how we look at Boyle's law. We want to understand what is happening if we alter something, right? And so in this case right here, we see that we might have X amount of volume, and if we were to decrease the pressure, then the volume would increase because there's not so much weight, force pushing down on those particles, and vice versa. If we said we need less volume, we need that to take up less space, well, we have to do something to increase the pressure, right? And there's, again, that inverse relationship. Assuming our constant, then assigning that constant a value of K, then what we can do is now bring both of those conditions equal to each other, and we get that form of the equation. P1V1 equals P2V2. It's pretty easy equation to work with, right? So that one's fairly it's fairly easy. Let's look at a problem. I've got something here. Let's just make something up. Let's just assume that you have an initial condition. All right. Assume you have an initial condition where the volume equals 100 liters. And then you have a new condition where volume equals 50 liters. There's some pressure, and initially you know that the pressure was equal to 5 atmospheres of pressure. Okay, I'm just making this up. I'm just making up numbers. And you can see I'm using numbers that are really not too difficult to work with, so that you almost could do this particular math in your head. There's no need for me to use weird decimal numbers and stuff like that, especially when we're learning something new like this. But it's never going to be this clear cut and dry. So let's think about it. This is our initial state. And this is our change state, the altered state, right? So that means this has to be P1 equals the, oh, I forgot to write 5 right there. That's 5 atmospheres of that. I think I may have said it. I just forgot to write it. Sorry. So 5 atmospheres. So we've got 5 atmospheres. Our initial volume we said is 100 liters. And here we've got a new volume, and all those same particles, assuming a constant, right? We're assuming that the temperature is the same, and we're assuming that we have the exact same number of particles, right? Same moles of particles. Now we have 50 liters. So the question is how much pressure does it take to reduce that volume for those number of particles staying constant from 100 liters to 1/2 of that volume of space, right? So go to Boyle's law. We've got P1 V1 equals P2 V2. We're solving for P2. So here we just do basic math like your algebra teachers taught you. And so we see that we get P2 equals P1 V1 divided by V2. This is basic plug and chug math. All right. So we've got P2 equals P1, which is 5 atmospheres, times volume 1, which was 100, right? 100 liters. Divide that by V2, which is 50 liters. Now, we won't really need a calculator for this, if you think about it. Liters crosses out. 100 divided by 50 is 2, right? Because it basically is 1/2. Or if it's on top right now, what's here is double what's on there. That's basic math, right? And so you can see that the pressure in the new system would be 5 times 2 would be a total of 10 atmospheres, and that makes sense. If we look at this graphical analysis here, all right, if we were to increase the pressure, so let's just say we're at any given point. We're at this given point here. If we were to, since this relationship is a direct inverse relationship, right? I know that sounds weird to say a direct inverse relationship, but it is directly inverse because we can say that the pressure equals this, okay? Then it makes sense that as if you were to change this by 2 units, you get a similar change in the variable. So basically, here's what we're changing is the volume. To do that, we had to, what happened was the pressure had to have changed. So that it does make sense that the math here is working out. And here's how you know the math is working out, and here's how you know that this makes sense. It's all about the units. Remember, everything has been about the units. These units crossed out. The only unit remaining is atmospheres, which is our unit for pressure. So if we were left with any units involving volume or any unit that other than atmospheres, that's how we would know that what we're doing makes no sense and that this relationship is not valid. But it's valid because it works out. Okay. All right. Pause and rewind and use this. Anytime you use Boyle's law, it's basically this. You can see it's essentially basic algebra. It's just setting 2 conditions equal to each other. All right. Hope that helped, and be looking at the next video. We got multiple videos in this series. We'll look at Charles' law, Gay-Lussac's law, combined laws, ideal laws. All those will be within the playlist for you to get to. Take care. Hope that helped. See you next time. Bye.